Hello. I'm just gonna be showing how I go about this question. Excuse me, sorry. So of course we have all of our resistors and we have our total voltage. So off the bat, we could tell that these two right here are in series circuit, connected by one pathway. So we know that the total resistance between the two is simply just them adding up, right? So then we have a new circuit that looks like this now, right? That's our new circuit after we put these in together, right? So this would be R34 now. Now we can tell that these two are in parallel circuits. So they're in parallel series now, right? So we use Kirchhoff's law, which is our total resistance between both resistors will be is equal to 1000, right? You add these two together and you should get around somewhere around 0. 0.0. Should get something like that. And then you just do inverse, and then you just take 1 over this, and then you just get that R234 is equal to 750 ohms, right? So now we could redraw the circuit again. Looks something like this now. Right? This being R234 now. R1. Now we condensed it and we could get our total resistance just by adding these two because they're now in series circuit connected by one pathway. So simply our RT is just the sum of these two, 1000 ohms. Now with our total resistance, we can solve for the total current, right? We have our total voltage, we have our total resistance. 100 volts divided by 1000 ohms. Simply just 0.1 amps. Now we want to find the voltage drop in every single resistor and the currents, right? Let's solve for the current for R1 first, right? It's the easiest one, right? Oh, let's solve for the total for the voltage drop in that. We know that it's in series circuit, right? So from here to all over here, it's gonna be 0.1 amps, right? And here it's series, so we know our I1. We're gonna solve for V1 now. So it's I1 times R1. So it's simply just 0.1 times a resistor, which is 250. And then when multiplied, you get V1 is equal to 25 volts. Okay. Now that we have that, oops, sorry. This is how I use it. This is how I view it. Now that we have a total voltage drop for the first one, we now know that all of this here will equal to what's missing, right? So we can just do VT minus V1 is equal to V2, because that our V2 is what we have left over. So just 100 minus 25, and we have that V2 is equal to 75 volts left over. So now we know all of this and this resistor right here will equal to 75 volts, and it will also have 0.1 amps. Now let's recap that. Excuse me. Okay. Once again, let's redraw it real quick. Let's just do a simple one. Sorry if it's a little messy. 1000 like I said again, all this we go 75 volts and row we go zero point 0.1 amps. So we know it's parallel circuit, right? From here to here it's parallel, meaning this right here will be equal to V2 will be equal to V3 plus V4. Because these two are in series. So that means that there's voltage drop, like Ohm's law says, or Kirchhoff's law says, right? Because they're in series circuit. But these two circuits, these two resistors, are in parallel with the 1500 here. So we have our total voltage right here. Sorry, excuse me. I'm going to solve for the current, right? We have a total voltage. So take our voltage, 75, divided by 1500, should equal around 0.05 amps, right? Just want to make sure. Yep. Okay. Remember, it's always important to remember these rules. Okay. Now that we have that current for this one right here, right? Once again, we said that this circuit right here, or this resistor, my bad, is in parallel with these two resistors. So, in a parallel series, current is not constant. It adds up. We know our total current is 0.1 amps. And we know our I2 is 0.05. So you can solve for these two are they're in series. So they're going to have the same current, right? Because they're one pathway, right? So then to find the missing series current, we're going to just take and then from this we find out that I1 is equal to 0.05 amps as well. Now having our I1, it's constant within these two resistors because it's series circuit. Now we have this means that our I34 will be constant, so then we could solve for the voltage drop in each. So then V3 is equal to V4 is equal to R1, R3, so I3. And this should equal 25 volts, 50 volts. Okay, that is complete. Now, we could check. These two add up to 75. These two add up to 75. They're in series, so this voltage drop, they add up. It's in parallel with this 1500 right here, right? So that means it's constant for both. 1500 is 75 volts, just how much this adds up to. And then once you condense it, 25 here, 75 volts here, adds up. You can always check. In this scenario here, we have 5 resistors, given the value for each, and we also have our total voltage. And this is how I approach it. So, of course, we gotta solve for total resistance. These two right here, these two resistors are in series circuit, right? We could tell because they're put together by one path. So instantly, using Kirchhoff's law series, you know that our total resistance for both will be equal to the sum of both. So then R34 is equal to 2,500 ohms, which could also be rewritten as 2.5k ohms if you want to do that. Right, so now let's condense it. Let's condense our circuit. So this will be turned into this now. Right. Sorry if it looks sloppy. This 10K, 500. Then we got that this was 2.5K, right? So now how I go about this is that now we see that these two are in parallel, right? So using Kirchhoff's law, we know that the total resistance between the two will be equal to the inverse of each. All right, if you plug this into your calculator, you should get somewhere around, see this, somewhere around, that's supposed to be a 2. Not sure. Somewhere around 0.005, right? So to find that, you take the inverse, 1 over 0.0. Then 1 divided by this number, you get 2,000 ohms. Right. Now, again, we want to condense the circuit. Right. Now we have this, right? Condensing it. We got the sum for these two. That this is R2, 2, 3, 4 now. And this is R1. And this will be this R5. Now we can tell that all this is connected by one single path, right? So it's on series, and it's just a basic series circuit from here. So total resistance is to the sum of, and we get that RT is equal to 3,000 ohms, which can also be rewritten as 3K ohms. Oh, excuse me, sorry, not 3K, 5K. Pardon me. Right. With this, we also have a total voltage, right? Now we can solve for our total current. Total current formula using Ohm's law. IT is your total voltage over your resistance total. Now our total voltage is 100. We just solve for resistance, 5,000. And you should get around 0.02 amps as your total current. Okay, now let's go back to the original schematic. Once again, I'm sorry if it's ugly. Okay. Here we have our total current, right? So that we know that the total current leaving here passes through the resistor. And because this resistor is in series, we know that our current for resistor 1 is simply just our total, which is 0.02. So then now we want to find the voltage drop in this resistor. Right? So we saw for using Ohm's law, V1 is resistance 1 times current 1. 250 ohms times. And you should get your voltage drop of V1 equals 50 voltage, 50 volts. Sorry, that's supposed to be 2,500, excuse me. Yep, 51. All right, and then we also know that it's in series here, right? Because if you condense it, it's all just one big circuit. One big resistor right here. Still one series, still in series. And even after all this current passes through, it all comes back to the total right here, right? So we can solve for V5 as well. It's again 0.02 amps times resistor. We get that voltage 5 is equal to 10 voltage, 10 volts. Okay. Now we have V1 and V5, right? We know that the leftover voltage drop, whatever's left over, all this here, all these three resistors here will be equal to that. So we can solve for that missing voltage by just simply doing, right? We know that this is true, right? Because if we all condense this down to one big circuit, it would be V234. So then if you want to solve for this voltage right here, it's Vt minus V1 minus V5. And we have this as 100 minus 50 minus 10. We get that our total voltage here is simply 40 volts. All right. Now, going back to the original equation again, or schematic, excuse me, we know that all this here is equal to 40 volts. Here, look, these two, it's just like the last problem we did. These two are in series again, and this one is parallel to these two right here. So, we know that the total voltage for this one is simply 40 volts, right? So then V2 is equal to 40 volts. We could write that down. Then that means we can solve for the current, right? So now solving for current for V2, for I2, we have our voltage 2 divided by the resistance of that. 40 volts divided by 10,000, which will just give us 0.004 amps, right? Now, bringing this back, okay. 0.004 amps, we know that our total, remember if this was one big resistor, then all this right here was one big resistor, our total through each would be 0.02 amps, right? Like this. So, again, this is parallel. This is parallel with these two. So it means that in the parallel series, current is not constant. So you add this plus these two. You have a total. So that means that we get to do this. Again, this one's I34. They're the same because they're in series right here. Look, see, right? So if you want to solve for that current, we get that I34 is around, right? And with this, now that we have our I3 and I4, we can solve for the voltage drop in these two. which is simply just the resistor times the current for each. Resistor 3 is 1,000 ohms times 0.016 amps. R4 is 1,500 ohms times 0.016 amps. And then if you solve for each, we should get that V3 is equal to 16 volts and V4 is equal to 24 volts. Again, always check your calculations. Yep, seems about right. Then again, you can always check. These two add up to 40, right? Voltage drop in a series circuit adds up to 40. Constant in a parallel. This adds up with R2 voltage, which is 40, 40. And then we have 50 up here and 10 here. Voltage drop, series circuit, add them up, it equals to 100 volts. And that's how you go with this question.